Good morning, everyone. The International Commission on Illumination, also known as the CIE from its French title, is devoted to worldwide cooperation and exchange of information on all matters relating to science and art of light and lighting, color and vision, photobiology, and image technology. With strong technical, scientific, and cultural foundations, the CIE is an independent non-profit organization that serves member countries on a voluntary basis. My name is Venkat Venkatramanan, and I am the past president of the Canadian National Committee of the CIE. The CNC is co-sponsoring this workshop, and on behalf of the CNC CIE, I welcome you all for this session. CNC CIE is the Canadian National Committee of the CIE with secretariat at NRC Ottawa. Membership of CNC CIE is open to all Canadians, and there is no membership fee. By becoming a member, you will have the opportunity to stay in touch with the latest international developments in standardization in lighting, color, vision, and related fields. Participate in the deliberations of the National Committee, and if you are technically knowledgeable, to directly contribute to the CAE standardization effort as well. Now, we have 4 speakers as panelists in this session. Deborah Garsman will open the session and talk about light, color, and design. Dr. Tony Esposito will be the next speaker and introduce modern concepts in quantifying color. Professor Mariana Figueiro will then talk about applying these concepts to lighting for better human health. The last speaker, Patricia Rizzo, will elaborate on how these concepts transfer in real-world products with a specific focus on color quality in lighting for classrooms and patient rooms. Once again, on behalf of CNC CIE, I welcome you all and hope you have an informative and engaging session. Now over to Tom Butters to introduce the speakers and moderate the discussions.
Thank you for the introduction, Venkat. My name is Tom Butters, and I am the Executive Director of the Lighting Agora. We are a consortium of independent expert consultants geared to meet all lighting needs of the industry and individual organizations. Today, we have 4 industry experts to provide 4 unique pieces on light, color, and. First up is Deborah Gottesman and light, color, and design. Deborah Gottesman has a unique contextual understanding of lighting from all perspectives. Her career spans over 30 years in all facets of the lighting industry, including design, engineering, management, education, and manufacturing. Since establishing Gottesman Associates in 1999, Deborah's creative, rigorous, passionate, and client-driven approach have brought award-winning lighting designs to a wide variety of satisfied and repeat clients. An electrical engineer with an MBA in real property, Deborah has successfully worked on projects in many sectors and has taught lighting at all levels to a wide audience, from students at colleges and universities to senior architects. Deborah currently sits on the International Technical Committee 359, the integration of daylight and electric light, for the Commission Internationale d'Éclairage, the CIE. Without further ado, here's Deborah Gottesman.
I'm going to talk about using color and light in design. But before we get there, we have to define what exactly is light. Well, light is radiant energy capable of exciting the photosensitive cells in the retina of our eyes, and through a sophisticated process of nerves, produces a visual sensation. That visual sensation is our sight. Now, the radiant energy has various wavelengths, where the shorter wavelengths are in the blues and the greens, and the longer wavelengths are the reds. Now, different light sources have different spectral power distributions, and some examples are shown here. So, for example, you can see that daylight is fairly balanced in all the colors, whereas tungsten halogen has very strong in the reds, but not very much in the blues, and where LED actually has a spike in the blue and is fairly weak in the reds. Now, we discuss color and light together because they are intrinsically related. It's reflected light that enables us to see. So what is color exactly? The definition of color is deep and vast, but from a lighting designer's perspective, color is simply the visual perceptual property of objects that interacts with the photoreceptors of the eyes. So the physical properties of an object, such as light absorption, reflection, and emission, are what give colors their appearance. The spectrum of the light source must contain the wavelength of the colored object for us to be able to see the color accurately. So in this example, where we have a balanced light source with a balanced spectrum, there's blue light in the spectrum, and the blue surface reflects the blue light and absorbs all the others. Now in this example of a high-pressure sodium lamp, the spectrum is strong in the yellow region and is almost devoid of the reds and blues. So most of the spectrum is actually absorbed by the surface and very little is reflected. So for example, if there's a blue car in that parking lot, it simply appears like a dark, almost black color, as you can see. So the critical takeaway here is this, that a color can only be perceived accurately if the spectrum of the light source contains that color. That is the intrinsic relationship between color and light. Now, one more note on this. These two kitchens objectively have a similar amount of light on their surfaces, but the white kitchen appears so much brighter, and that's because it's reflecting the full spectrum, whereas the brown kitchen is mostly reflecting the light in the red and orange part of the spectrum. So the brown kitchen will always be perceived as darker. Now there are two metrics of light that also need to be understood. The first is that of color fidelity, how accurately colors are seen under a light source. Now you may be familiar already with the Color Rendering Index, or CRI, which is the old metric. We would evaluate those pastel color swatches under a light source and score the light source on a scale of 1 to 100. So a CRI of greater than 80 was considered good, 90 was considered excellent, and anything below 70 was considered poor. So CRI was pretty easy to use as it helped define color fidelity with only one number. But of course, there are limitations. It's a very imperfect metric. It's based on a limited palette, and it gives us no indication of which colors are saturated or desaturated, for example. Now, color fidelity is really important because we can't adapt to poor color rendering. Those strawberries on the left will never look right to us under that light source. And if you were the retailer trying to sell those fruits and vegetables, clearly you want them to be appealing. Now, today we have a much better metric that Tony will be discussing in his talk shortly. The second metric for the color of light is called color temperature, which defines the warmth or coolness of the light source, and it is independent of color fidelity. Now, color temperature is expressed in degrees Kelvin, where the lower numbers are warmer. So, for example, 3000 Kelvin is considered warm white, and the higher numbers are cooler. So, daylight at noon is around 5000 Kelvin. Color temperature is independent of color fidelity, as I said earlier. You can have a high color fidelity with warm or cool light sources, and you can have low color fidelity with sources that are warm or cool as well. So it's not an exact formula, but higher color temperature lighting, so that in the cooler, is often perceived as open, expansive, energizing, and public. Whereas low color temperature lighting, in the warmer, is often described as private, intimate, romantic, and residential. So now let's discuss how color can be used in lighting design, and first we'll look at color temperature, which can be used to enhance any space. Now here at 3 Church Street in Toronto, we used cooler color temperature of 3500 Kelvin to highlight the cool aqua-colored dental molding, while we used a warmer color temperature of 2700 Kelvin to light the warm red brick. In this Forest Hill residence project, we used warmer color temperatures throughout the home, which is pretty typical here in North America, so around 3000 Kelvin. Now this cozy den space is where we would enjoy watching television or sharing a drink at the bar with friends. But in the adjacent sports court that you see on the right, we moved to a cooler color temperature of 4000 Kelvin. The cooler color temperature is more energizing, so that the lighting assists with transitions to a different type of activity, providing a visual cue that the sports court is an active and energized space. Now, of course, we can also use actual colored light to enhance a space. It brings visual interest, character, and entertainment. In this case, at the Ontario Association of Architects headquarters, the colored light also enhances the character of the architecture, drawing our attention to the interesting details. In this Silicon Valley residence, the client wanted to create different moods in the bedroom, so a single strip of color over the bed was an ideal solution for this application. Similarly, in the great room, color was desired to be able to change the ambiance, so a splash of color was added there as well. And note, this is showing you a purple color of light, but in fact, it is a full color changing strip, so it could be any color to suit any mood. So whether it's a play of color temperature or using colored light, light and color are a powerful tool to enhance any space. Thank you.
Thank you, Deborah. That was excellent. And it certainly sets the stage for our next three panelists. Up next is Tony Esposito with Light, Color, and the Importance of Modern Lighting Metrics. Dr. Tony Esposito is the founder and head research scientist of Lighting Research Solutions, a lighting consultancy providing services in research, education, and development. Tony holds a doctorate in architectural engineering from Penn State University with a minor in statistics. His specialties include color science, color discrimination, IES TM-30, human factors research methods, circadian metrics, and spectral modeling and optimization. His primary research goal is to develop an accurate and intuitive color discrimination metric for applied lighting. He currently serves as the co-chair of the IES Color Committee and previously led the task group that developed IES TM-30 Annex E, a set of recommended specification criteria meant to ease the use of TM-30. Now, Dr. Tony Esposito with Light, Color, and the Importance of Modern Lighting Metrics.
Hello and welcome. My name is Tony Esposito. Thank you for joining me today for what will probably be the quickest presentation of my professional career. I'm going to talk about color rendition today, so let's just dive right in. So I want to talk quickly about the transmission of light, because I think it'll provide a very informative point that I'd like to make forcefully. So the transmission of light starts with a light source. So here we have a light source that emits radiation. That radiation will land on an object. Here I'm showing a red apple. Some of that radiation will be absorbed, some will be reflected, and the reflected light will go into an observer's eye, and they will make a judgment. That looks good, that looks bad. We quantify this using something called the spectral power distribution, the spectral reflectance distribution of the object. And here you can already see why this red apple will like to look red. You can see that it reflects a lot of long wavelength radiation, which we tend to perceive as red. We multiply them together, and this is the light that enters our eye. And we can see now why we perceive that red apple to be red. What's important, though, is if we take our light source here, we're having daylight, and imagine that we filter light coming in to get rid of the long wavelengths, the so-called red wavelengths. And then we illuminate that same object, but this time the object does not have any long wavelength radiation to reflect. And so that object will appear gray or dark, and it will not look very good. And so we have to, based on this, we have to assume that color is not an intrinsic trait of objects. Okay, this is a really important point that may be obvious to many of you, but it's important here to reiterate. Color is not intrinsic to objects. The color that we perceive, color perception, is a human phenomenon that's the result of the light and the object interaction. So as a lighting researcher and scientist, an educator and lover of light, we can ask this question: how do we quantify the impact of a light source, the color rendering impact of a light source? And it turns out that this is not an easy question to answer. And so we can first ask, I find it easiest to try to understand these, the sort of multiverse of the ways that a light source can impact color by asking questions. And so we might first ask, how similar on average does my light source render colors compared to a standard reference illuminant? We call this average fidelity, and there's a measure called IES TM-30 RF that we use to capture this. If you're familiar with color rendition, the legacy measure of average color fidelity is the CIE General Color Rendering Index, or often more informally called CRI. We can ask how similar does my light source render specific colors like red compared to a standard reference illuminant. We can call this local color fidelity, and we have a measure from IES TM-30 called RFH1, H1 being the red hue bin. We could say on average, for many colors, does my light source increase or decrease the chroma of objects relative to the reference illuminant? We call this gamut area or average gamut area, and we can quantify that with a measure called IES TM-30 RG, G for gamut area. We can ask, does my light source increase or decrease the chroma or saturation of objects of specific colors, for example, red? We call this local chroma shift, and there's a measure again from IES TM-30 called RCSH1, CS meaning chroma shift, H1 being the red hue angle bin. We can ask then, does my light source allow me to distinguish between similarly colored objects when we view them simultaneously? This is a concept known as color discrimination, and there's a recent research proposal by me and Dr. Kevin Hauser called the light source error score, RD. We can ask, will my light source cause mismatches between a set of objects that were previously metameric with respect to the reference illuminant? We call this metameric mismatch, and there's a recent research proposal called the Metameric Uncertainty Index, RT, of which I've been a co-author. Then we can ask, how does the amount of light impact color rendition? This is something called the Hunt effect, because we know that as you decrease the amount of light falling on an object, it will cause our perception of this object to decrease in saturation, or vice versa. The more light you put onto an object, the more highly chromatic, saturated, or vibrant it will tend to appear. These ones down here are research proposals or work in progress, and these measures up here are from, as I mentioned a couple times now, Technical Memorandum 30, published in 2022, of the Illuminating Engineering Society, often referred to as IES TM-30. You can go onto the IES website right now and download that document for free if you want to learn more about the nuances of those measures. So overall, I mean, we can see quickly that color rendition is quite complex, and it's only one of the things that lighting designers need to consider when they're doing a design. And so we could see that the job of the lighting designer is really quite difficult. And so my job as a lighting researcher and educator is to increase the specificity of lighting design and to increase overall quality of lighting in the built environment, but to try to do so in a way that's not impossibly difficult to specify or implement. And so that's been the challenge of my career, essentially. So looking forward to taking questions. Thank you so much. If you want to contact me, my email is there on screen. Thank you.
Thanks, Tody. That's fascinating. Up next, we have Dr. Mariana Figueiro with Light, Color, and Health. Dr. Figueiro is the director of the Light and Health Research Center at Mount Sinai and professor in the Department of Population Health Science and Policy at the Icahn School of Medicine. She is well known for her research on the effects of light on human health, sustainability, circadian photobiology, and lighting for older adults. Dr. Figueiro is a fellow of the Illuminating Engineering Society and the author of more than 140 scientific articles in her field of research. She has brought attention to the significance of light and health as a topic of public interest through her TED-Med talk. This is a fascinating topic, and I want you all to welcome Mariana Figueiro with Light, Color, and Health.
Hello, everyone. My name is Mariana Figueiro, and I'll be talking about light, color, and health. We do know that light affects three of our systems: the visual, the non-visual, and the message. And the presentation here is mostly focused on the non-visual systems because they're most related to health. So within the non-visual systems, we have the phase shifting, or the fact that light is the primary synchronizer of circadian rhythms to the local position on Earth. We have a biological clock that is slightly longer than 24 hours. So what light does, especially daytime, morning light does, it resets the biological clock daily to allow us to run with a clock of 24 rather than 24.2 hours. Now, if we don't get enough light during the day, or if we get too much light in the evening, or in the nighttime, like shift workers, light can also be a major disruptor. And disruption of circadian rhythms has been linked to a series of maladies, from poor sleep and poor performance all the way to increased risk for diabetes, obesity, cardiovascular disease, and even cancer. So in terms of the spectral and absolute sensitivities of the circadian system for phase shifting, we know that we have been working with a metric called circadian light and circadian stimulus. We know that the spectral sensitivity of the circadian system for acute meltdown suppression and for phase shifting of the biological clock has a peak sensitivity at short wavelengths. So we're pretty much blue sky detectors. Now, we also need higher amounts of light. So just talking about spectrum is not enough. We really have to talk about the absolute sensitivity, and that is what circadian stimulus does. It combines both the spectral and the absolute sensitivities. So we need more light to activate the biological clock than we need, for example, to see. Now, in terms of the direct effects, we do know that light has an acute alerting effect on people. It's almost like a cup of coffee. Now, for that, it doesn't have to be blue, even though blue is also alerting. We have a series of studies, and others also have studies showing that if you remove the blue light, you don't suppress melatonin at night, but you still maintain alertness. So for alertness, you don't need to have just blue light or short wavelength light. In fact, our study shows that saturated red light, peaking at 630 nanometers, will decrease self-report sleepiness, will increase performance, so there's going to be faster reaction times, and will also affect brain activities. And here are data from our lab. We collected that in the afternoon, and we looked at alpha power. So an increase in alpha power means you're getting sleepier and more tired. So what we showed was both blue and red lights, and these are 630 nanometers and 470 nanometer lights at 575 and 150 lux at the eye. They reduce, and the higher light levels, the more the reduction of the alpha power, suggesting that there was an increase in alertness. But we saw that effect with both the red and the blue lights. We're also doing some work with Mayo Clinic, where we are putting people in fMRIs. So we're doing brain scans and looking at basically blood flow in the brain. So an increase in blood flow suggests that there's more activity in the brain. And we saw that compared to a baseline in dim light, giving people red light or giving people blue light, both increases that blood flow, suggesting that there is an increase in brain activities with both the blue and the red. Very consistent with what we had found in our lab as well. So then we have transferred that information to the field. And the idea is that you give 24-hour operators, in this case, we're Train Control Center in Istanbul, and it's a 24-hour operation. So you give the morning blue highlight levels. In that case, it couldn't be too high because they have a lot of screen use. So we tend to use the saturated blue to deliver that high circadian stimulus during the morning hours. And then during the afternoon hours and the evening hours, we reduced the circadian stimulus, but we kept the alerting stimulus with the red light. And one of the results that we found was that this lighting schemes has improved their sleep disturbances. So PSQI is a measure of sleep disturbances. So a high number means you have sleep disturbances. So what we saw that with the intervention of that 24-hour lighting scheme, that we have a reduction in the sleep disturbances. And we also saw a significant correlation in the amount of circadian stimulus they get in the morning and how well they sleep at night. So more light in the morning leads to better sleep at night. We also worked with shift work nurses. We recruited 45-day shift nurses and 45 night shift nurses. And we looked at a series of outcome measures. We exposed them to, there was a baseline, and then there were 2 weeks of either blue light, red light, or a dim white light that was used as a control. So they were exposed to all three conditions at separate times. And they were exposed to the light for 30 minutes at start, middle, and end of the shift. So here are the results of the performance tests, which were very interesting. We saw that with the red light, there was a significant decrease in response times, which means they responded faster, so they improved performance at the second and the third time in the shift. So in other words, in the middle of the day and at the end of the day, when they're more tired, the red light helped them improve performance. And the same thing happened at night. In the middle of the night, when they are more tired, we did see an improvement in performance with the red light exposure. I do want to briefly talk about the fact that red also has meaning and evokes emotions. And it may be that that response to our emotions is what's leading to that alerting effect of light. There are studies showing that people that are wearing red t-shirts, for example, appear to be angrier than wearing more gray or blue t-shirts. There was also studies showing that they were measuring force grip, and when the hand grip was red, that people were actually exerting more for force, suggesting that again that they were responding to that colored red. So we know that colored light can have impact in humans in various ways. In terms of the circadian system, blue light is maximally effective at promoting entrainment, and blue light can also elicit alertness or an alerting effect in humans. Now, the research also supports that our intuitive reaction to red, in our case, we are studying red light, and we're seeing that red light is evoking psychological and physiological effects in humans. And I think I want to end with that quote from Dr. Andrew Elliott, where he says that red is a danger cue, so your body reacts as if it has just seen a threat. What happens when your body sees a threat is it immediately automatically mobilizes energy to flee or flight. So it would be your flight and fight system. And we think that that is what's eliciting that direct acute effect of the red light. Nevertheless, I would like to urge everybody to think beyond blue when it comes to light, color, and health. And I think my colleague Patricia Rizzo will also talk about some of the applications. With that, thank you very much for your attention. And I look forward to the discussion.
Thank you, Mariana. That was truly fascinating and easily one of my favorite topics of light. Up next is Patricia Rizzo, and she puts it all together in light, color, and application strategies from classrooms to patient rooms. Patricia Rizzo, MSc, is the healthcare segment manager at Axis Lighting. There, Patricia integrates the latest global research and design principles into technology advancements, applications, and product design, with a focus on circadian lighting and healthcare solution. She draws on the expertise of specifiers and sales teams who have firsthand knowledge of the customer to drive the development of products required by today's stringent healthcare environments, and engages with hospital end users to listen to and address their needs and concerns. Educator, researcher, lighting designer, and program manager are all but a few roles she has enjoyed throughout her 22-year career. Prior to her position at Axis Lighting, she spent over 4 years as senior lighting applications developer at Philips Research North America, and 15 years at the Lighting Research Center as lead researcher, design program manager, and adjunct associate professor. Please welcome Patricia Rizzo with light, color, and application strategies from classrooms to patient rooms.
Good morning. This presentation is really a tale of two spectra that can play an important role in our lives. One that has an alerting effect for focus and learning, and one that does its best to prevent alerting, to allow patients a safe return to sleep while providing a guiding light for safe navigation. Axis Lighting strives to advance the practice of lighting through its support of global research and the leveraging of results into product development. And working together with the Light and Human Health Partnership of the Mount Sinai Light and Health Research Center, Axis has been fortunate to do just that. Classroom lighting involves balancing stimuli. When we are designing classrooms in general, the challenge is to accommodate the needs of the diversity of students in any one group. While ages may be similar, their level of concentration, ability to focus, sensitivity to visual and other environmental stimuli varies greatly. There is even a section of the WELL program that focuses on education, WELL for Education, kindergarten through 12. It recognizes the need to support cognitive and emotional health, goes on to state that 1 in 3 students can experience depression, anxiety, and worse, and that improving indoor environmental conditions can improve cognitive performance scores. It sets circadian metric targets similar to the main WELL standard, with emphasis placed on the amount of light at the eye and duration of at least 4 hours a day, starting no later than noon. But when a classroom is dedicated to children with special needs, consideration must be given to the delivery of light, how to reach those recommended targets. Increasing light levels alone may be too harsh, may overstimulate a child with autism, for example. Classroom lighting in general may be perceived as too bright by these children. Axis worked with LHRC researchers to provide a luminaire system for one of 2 special education classrooms as part of a pilot study at a middle school in upstate New York. By adding saturated blue, the design boosts circadian impact with minimal illuminance increase and energy use. It creates a less stimulating environment, but still meets circadian needs. The goals of the project were to use blue light to create both a stimulating and calming effect, enhance a daytime stimulus effect, which could result in better sleep at night and therefore better ability to focus during the day, but minimize the need for bright white light, improve focus on learning, but avoid overstimulating the children with light, and make the lighting system easy to operate for teachers by programming preset scenes. Axis Lighting worked with the LHRC to provide a lighting system with the desired spectral qualities by creating a lighting design that included a layer of white ambient light and a layer of blue light on a separate control. The teachers were able to control how much light and at what part of the school day to introduce that light. The addition of recessed linear tunable color luminaires that were able to provide a peak wavelength at 460 nanometers, alternating with recessed tunable white light 2x2s, created a balance within the classroom space. Overall, the children responded positively to the dynamic lighting with regard to sleepiness and focus. This is just a first step, but the project can be used as a model for other schools to follow. At the other end of the spectrum, let's look at one of the big issues in patient rooms, falls. Whether in the US or Canada, falls account for most injury-related hospitalizations. They inevitably increase long-term chronic pain, cause loss of independence, cost health systems billions of dollars, and they increase length of hospital stay. One way to reduce falls, then, is to try to reduce the length of stay. Circadian supportive lighting, providing strong light-dark contrast, should help. High stimulus by day to low stimulus in the evening, and darkness before bedtime to promote entrainment, improve sleep quality, and potentially benefit recovery. Minimizing or eliminating short blue wavelength exposure in the evening by using amber to red in the 580 to 615 nanometer range would be part of that plan. A family of products can contribute to a falls prevention strategy. In addition to amber nightlights from wall sconces, amber step lights, they can guide patients from bedroom to bathroom, while vanity mirror nightlight allows patients to navigate the bathroom without being disturbed by a bright white light that would prevent them from returning to sleep easily. But one piece has been missing from that family of products to complete the strategy. How does the patient recognize the location of the door in the dark? When I was at the Lighting Research Center over 15 years ago, we had started studies to test the effectiveness of a novel night lighting system that would not only help with navigation, but help patients balance themselves and stabilize their posture when going from sitting up in bed to standing on the ground to make their way to the bathroom. It provided visual cues, vertical and horizontal lines of light to help a person orient themselves, gain postural stability, and more easily identify their destination, which was the bathroom doorway. It provided enough light to see, but was not so bright as to prevent the person from falling back asleep. It used a visually comfortable color of light, amber, to contrast with the dark surroundings while also minimizing circadian disruption. And it balanced the luminance of low-level night lights closer to the floor so obstacles were more visible. We've now developed that missing link, an amber night lighting system that outlines and clearly delineates the doorway. Easy to install, low luminance, low glare, and modular, because perhaps only one or two sides are feasible, and visible from many vantage points in the patient room, depending on the relationship of bed to bathroom. The image on the left zooms in on the effect. The image on the right illustrates both prototype versions installed in our patient room demonstration at Axis headquarters in Montreal. A surface mount for retrofit situations around the left door, and recessed for new construction around the right door. Here we see the patient's view from bed to bathroom door in our hospital room demo, but finally, an actual recent installation at a New York City hospital. All hospital rooms being different, spatial constraints in this one allow only two sides. The system is dimmable to be able to set a comfortable luminance level and will be operated on a timer from evening to morning. So this snapshot has been a tale of two spectra, both important pieces of very different applications for very important people in our lives.
Thank you, Patricia. That certainly wraps it all up and puts it into an application perspective. Very well done. We're now going to take just a few moments while we all come back on live, and we'll be taking a few questions for the remainder of our time.
Hey, good morning, everybody. Do I have our panelists here up and ready? Hi, Deborah. Yeah, so questions have been coming in. We thank you. Please continue to send them in, and I'll be doling them out, and hopefully we'll be able to get to as many as possible. Let's go in the same chronological order as the delivery. Shall we start with Deborah then? Deborah, do you have a question there? Could you read it out and then respond to it, please?
Sure. The question was, I read it earlier. Do we have a go-to color temperature for design? And if not, what process do we use to decide? So when it comes to color temperature for interior illumination indoors, it's really about preference. North America, residentially, we prefer 2700 or 3000 Kelvin. But there are other places in the world where they prefer 5000 Kelvin. So it's not a right or wrong. And the process we would go through when we do a residential design is we would show the different color temperatures and have the homeowner pick. But pretty typically, we've never done a home that was higher than 3000 Kelvin. Now, when it comes to outdoor lighting, that's a different scenario altogether, because we want to be dark sky friendly, and dark sky friendly has a number of components to it. And one of the components to protect flora and fauna is that we stick to 3000 Kelvin or warmer even. So that, and in some cases that's mandated as well.
Okay, wonderful. Thank you very much. Next, Tony, do you have a question there from the audience?
I think I do. Can you hear me?
Yes, we can.
So I have a question here about the sort of the adoption and acceptance rate of TM-30, which is a good question. So TM-30 has been out for a while now, and I think the lighting industry tends to move slow in general, but I think TM-30 has already seen some really good uptake. So it's currently included in a bunch of different standards and qualification documents. So it's part of the Unified Facilities criteria for medical facilities for the US, I think, Department of Defense. It's made its way into the well building standard, into the Design Lights Consortium technical requirements for their qualified products list. And I think a couple other. We've seen it make its way into manufacturer spec sheets, and there are some manufacturers who are using it already and some lighting designers who are using it already. So I think it's seen pretty good acceptance for having been around for just a few years.
Okay. Wonderful. Thank you very much. Hi, Mariana. I know you have a couple of questions. I saw a number of them coming in. You're on mute now.
We should know this by now, shouldn't we? After 2 years, it never ceased to amaze me. All right, so I think I'm in order here. Is that the one you're referring? Is there any long-term effects of using red that enables agitated emotional response? There hasn't been a lot of work with long-term effects of red. My recommendation would definitely be not to keep people in a red room. I think that obviously, you know, even with bipolar, any type of light can get people agitated. So you can always have negative effects of long-term exposure to these types of light, depending on the population. The other very interesting thing that we're now starting to look into it is that you also may have an adaptation to the red light. So in other words, if you're exposed to it for a long period of time, that acute effect may fade a little bit. So it would be much more interesting to expose people, say, to half an hour and then give them a break for half an hour, then give them another half an hour. So there might be patterns that we can develop that will be more effective at the alerting effects, and that it would minimize any chance that there would be this long-term effect of the red light.
Okay, thank you very much, Mariana. Appreciate that. Patricia, I think this is going to be our last question because we're over already.
Okay.
But, please.
Quickly, the question I have is, in patient rooms, how do you approach the conflicting needs of the patient and the hospital staff during evening hours? That question comes up all the time. Staff needs very low light to check a patient during the night. We call it night check mode, where it's about 1%, just so that they can make sure that they're breathing, but it's not enough light to disturb them and wake them up. But for nurses at their station, certainly they need enough light to do their tasks. So there may be a minimal illuminance level so that they can see, but it may not be enough to give them a boost during the night, which they might require to stay alert. So if there's a separate break room where they can have a task light with either red light, which Mariana talked about, which has an alerting effect but won't alter their circadian rhythms, or blue light, which has an alerting effect but would affect their sleep-wake cycle and their schedule at home the next day, that would be one solution. So to provide separate areas where they have both task lighting and circadian effective lighting.
Okay, thank you very much. Thanks to all the panelists who agreed to participate on this. I also would like to thank the CNC CIE and the CRSC for inviting us to participate in this wonderful event. So I'll pass it over to the moderators. Thank you guys. Thank everybody.
Thank you.
Thank you guys so much. That was a brilliant panel, very fascinating. There are some questions in the chat, so you're free to continue the discussion in the chat.